Today we will introduce Aztec Network and how Aztec preserves privacy. First, what is Aztec Network? Aztec is a privacy-first zero-knowledge rollup on Ethereum. That means it's the only layer 2 built from the ground up to be fully privacy-preserving. To understand the paradigm-changing nature of private transactions and why it's important to build privacy directly into a network's architecture, we have to first discuss why Ethereum is not private. The most primitive transaction on Ethereum is sending Ether from one account to another. The way the network keeps track of this is by incrementing one account's balance and decrementing the others. In other words, the ETH doesn't really move in any sense. Let's look at an example transaction in detail. Say my man SnoopDogg.eth wants to send a transaction to KozomaMetasci.eth. Here's how it shakes out. Snoop starts with 100 ETH and his account is debited 20 ETH. Kozomo starts with 0 ETH and his account is credited 20 ETH. Snoop's ending account balance is 80 ETH. Kozomo's is 20 ETH. Transfer complete. We can see a representation of credits and debits for each account right on Etherscan.io, with the ins and outs tracked in public for everyone to see. You can see the obvious problem here. Not only can we see all account transactions, we can see all the amounts, assets, and counterparties. That's in fact the power of public blockchains. Due to their public nature, they are eminently auditable and verifiable. But that means if someone's privacy is compromised, whether intentionally or by accident, we know their entire transaction history. So how to solve these problems? This is so easy to solve. Just encrypt the accounts, balances, and owners. Except let's actually talk through how encrypted accounts would work. Recall the ledger from before. With encrypted accounts and transactions, it would instead look like this. Back to our businessmen Snoop and Kozomo to help us figure it out. If they need to do a transaction, they'll have to interact, since the network can't help check that they did a valid transaction. And Snoop initiates the interaction. Snoop requests Kozomo's encrypted account state. Kozomo sends the encrypted state to Snoop. Snoop decrypts Kozomo's state, confirming the pre-transaction balance. Snoop sends an encrypted payment to Kozomo. Kozomo sends his updated encrypted state to Snoop. Snoop decrypts Kozomo's new state, confirming the post-transaction balance. At the end of this dual-sided dialogue, neither party has convinced the rest of the world of anything. They've only mutually validated their one transaction. Next, what an ownership change looks like for an encrypted note. When an Aztec transaction processes, rather than doing an account balance update, the network simply reassigns ownership for a given note. Well, it turns out it's way easier to encrypt a note, because it really only needs two things written on it: how much it's worth, and who it's owned by. When it changes hands, you scribble out the old owner's name and write the new owner's name. The transfer on Aztec is not public, which truly protects the privacy of both parties. What the state of the system looks like to an observer, the values and owners of each note fully encrypted. To protect their mutual privacy, Snoop publishes the transaction with a lock that he knows only Kozomo can unlock with his private key. The analogy here is kind of like putting the note in a little lockbox. Of course, they both know what's in the box, so Snoop has to trust Kozomo. To ensure nothing fishy happens in step 1, all Snoop needs to do is prove to the Aztec that the two notes he intends to create are equivalent in value to the two notes he intends to destroy. In order to prove that the output notes, C plus D, are equivalent in value to the input notes, A plus B, Snoop generates a zero-knowledge proof locally, in his browser. The black magic of ZKPs? Means he can prove the equivalence A plus B equals C plus D without revealing any of their individual values. Aztec then validates the proof and says, by the powers of zero knowledge, this must be true, at which point the smart contract destroys the two input notes, generates the two output notes, and records the new output notes as an encrypted commitment in the note registry. It's worth discussing how ownership of notes is proven in Aztec, which has analogies to Ethereum world. How do you prove you control access to an address in Ethereum? You sign a message using your wallet. In order to send notes that I've proven I own, an entirely new Merkle tree is created. Once the Merkle roots of both the note tree and nullifier tree have moved to new values, those roots are published on Ethereum's main chain and the transactions are deemed recorded. I hope this gives you a solid grounding for understanding why privacy is challenging. We need to verify that transactions are legitimate and properly executed without violating or exposing user data. These unique constraints mean privacy-preserving architecture must be constructed from the ground up. Aztec is the only Layer 2 built this way, with privacy protected by its core architecture and facilitated by the magic of zero knowledge. That's all for today's video. Thank you for watching. See you next time.